is, but then we figured out it is accorded to the schedule of the train. So we saw these are perturbations coming from vibrations of the train. What we see here, this looks very nasty. This looks nasty because unfortunately here the vacuum during observation was not perfect, so air came in, oxygen came in, and it came immediately. We had some kind of pollution or oxygen effects. Also to show you all these things on the nanometric scale behave different as you expect them in the macroscopic world. Here is just another setup. Maybe I skip this slide because it's not so interesting. Interesting was more to see the different types of glass, how they behaved for the reflectivity measurement that we did here. And we saw here typically all these materials, they show a different behavior. However, we could all structure them in the nanometric scale, and they should all more or less this antireflective behavior. However, when we come to calcium fluoride, what I mentioned at the very beginning, fabrication processes must be totally different because calcium fluoride, as I said, is a crystal, and crystals cannot be etched in an isotropic process because you will not get good results. So what we did, we combined these two processes. One process is a classical chemical approach. However, we combined it with a milling effect, means we projected, we shot reactive ions on the surface in order to have also a mechanical effect in order to dig out single molecules. And here, for example, you see this process starting first with the surface baking 30 minutes at 200 degrees Celsius. This in order to become the surface clean. It must be perfectly clean, so you cook it first, or boil it, bake it at 200 degrees. Then we have a 60 nanometers PMMA layer on it. This is our photoresist. Then we have a chromium layer of 30 nanometers, and the rest is 4 millimeters bulk material calcium fluoride. And then we exposed it to E-beam, electronic beam writing. Then we have this structuring here, and then by reflective etching, ion etching, we etched it here in the material and then by stripping away then the chromium layer, we have this structure. And you see here the etching rates. For the chrome, we figured out it's 1.2 nanometers per minute. But also, this looks here nice, because it's just one figure, but it took us 2 months, 3 months in order to figure out this number, because it changes every day when the weather is different, if there's a different operator, all these things. This is all something that you have to keep in mind when it comes to real products. In theory, this is nice, but if you have to produce every day such kind of structures, you have to have exact numbers, you have to have exact processes. So you have to exclude as much as possible all kinds of problems that could rise up. So also here, this second indication here of 2.9 nanometers per minute is something of a work which took us several months in order to find this out. The result then is very interesting. You can see here, we realized it looks a little bit nasty, but it is very unique. It's a calcium fluoride substrate with structures, line structures here of a width of 120 nanometers. And if you calculate here, from here to here is about 40 nanometers. So we can come down to magnitudes of 40 nanometers in calcium fluoride. And that this works showed us also for this application at 193 nanometers, which is still today used for production of semiconductor devices. We have these results, and we can see here we are below 1% of reflection, and we claim this is world first anti-reflective coating in calcium fluoride at 193 nanometers. Nobody has before shown similar results, especially not when it comes to real applications, when it comes to industrial applications. So let me focus or summarize this sub-wavelength application surfaces. First advantage, of course, the results and experience showed that clearly show a large potential to realize a new generation of optical elements such as anti-reflective gratings, polarizers, resonant filters, or DWDMs, which are used for optical communication technology. And within nanotechnologies, processes were developed to a level of scientific excellence and according to industrial needs. And the results from nodes are a substantial contribution to better understanding and of a feeling of the nano world with respect to optical industry. And the word feeling is maybe the most important one. Optical technology or nanotechnology has to do something with feeling, not with a sentimental feeling, with a experience, with a hands-on touch, the material experience. When it comes to reality, that's the important point. And Node means this project made clear that the difference between calculation and simulation on one hand and production and processing and handling on the other side are to be respected, and that's something we have to work on, and that's what makes optical industry all over the world rather skeptical to continue currently in big efforts. They will continue, but they are a little bit disillusionated. There comes another effect. I mentioned before the effect of pollution. I mentioned before all kinds of surface effects. And that's a third project I would like to show you here because it plays the same importance of role. This is the so-called non-wetting coatings. The abbreviation is NOCO. And such kind of non-wetting coatings for precision optics we developed here together with Patrick Hoffmann, a friend of mine from the Institute of Biomedical Imaging and Optics. And the requirements from industry were the following. First, they wanted to have a repellent with respect to water, organic fluids, dust particles, and a so-called static contact angle of at least 120 degrees. I can explain afterwards what it means. It should be applicable on glass and on fused silica surfaces with a Swiss Optic, this is a company, standard according anti-reflective coating. And there should be no decrease in surface quality according to ISO 10110 part 7. Don't worry, I won't go into detail of this standard. If you are interested in, I will certainly answer your questions. And the transmission decrease should be smaller than 0.5%. And of course also the adherence of the coating should be consistent according to the MIL standard E12397. For those who have worked in the field of defense, they know that these standards are all over the globe used, MIL standards. And of course it should be resistant to weathering, and it should be applicable to all optical surfaces, geometries, spheres, aspheres, plane surfaces, and of course also diffractive elements. And of course, batch processing should be possible. So let us now come back to the problem I initially mentioned. Tonight, you're gonna go home probably with a car. And if you go to the west, you're gonna have the face towards the sun. And then you're gonna have for the following problem. An uncoated lens, and I suppose your window of your car is uncoated. And it is certainly very smooth, but it's not as smooth as indicated here. It is a typical indication as we use it in optical industry. It's a typical optical surface. So if the sunlight comes, what happens? We have a lot of dust, and then you have a lot of stray light. So you don't see anything. And traffic is already dangerous in India. However, when you have stray light, it is even more dangerous. So you should think about maybe a coating of a non-wetting coating on your car also. So then of course there are friends from biology. They say, okay, there is the lotus effect. Of course, there is. However, pay attention. Let us look how lotus surfaces look like. You have here these plants, maybe even on the campus. I have to go to botanic gardens in order to find them. Fortunately, there's the internet, so I find also the surface of such kind of plants in the internet. And if you look closer to such kind of lotus leaves, you're gonna have such kind of structures. They look beautiful at afar, but at closer, they look horrible. They look really disgusting. So, and if it comes to optical surfaces, this lotus effect is not a good idea. You see, I just added here because there are people claiming that the lotus effect would be for optics fine. I say no, it's not correct because these guys didn't understand nanotechnology. Because sun comes and what happens? We have stray light anyway. Because Rayleigh scattering and Mie scattering, if you have ever heard about these effects, depend on the size of the effect of the element who strays the light, and when it comes closer or smaller to nanometer range or micrometer range, then you have these stray light effects. So it does not really help. It's certainly effective if it comes to, let's say, toilet materials for hygienic reasons. That can be a nice idea, but please not for precision optics. For glasses like this, possibly there's no problem, but for precision optics, please don't. So what can we do? Lotus effect does not really help since it increases even scattering on that level. So we have to figure out an optimum between non-wettability and optimum roughness, because these lotus leaves, they have a certain roughness in some way. So there was an idea with a friend of mine who's a chemist, I'm not a chemist, who said, let us try CVD processes with gas phase salinization on glass surfaces with perfluoroalkyl salines. Don't worry, I'm not a chemist either. I believe him just that he did a good job. But I understand that this works. It's easy to explain. If you just look at this molecule that we have here on the left, it's a funny molecule. It looks a little bit like a plant, maybe even as a pepper plant. It looks like a plant because it has a tripod, 3 atoms, the green ones, the chlorine ones, which can be attached to the surface. Now you have a tripod. And then you have a tail, like a plant. And this tail is made of carbon and of fluoride, and in this, or silane and fluoride, and this way it is like a hair, or you know, from animals. You might ask, some animals, they never get wet, even though they will be in rain or even in the sea, because they have a special type of fur, which in principle works a little bit like this. These molecules are very repellent, and you can steer the repellence by the density of these molecules as you attach them to the surface. And the density is mainly created by the chemical percentage of possibilities to attach these 3 chloride elements on the surface. So what we do, we have to hydroxylate the SiO2 surface. That's what we did here. This was a chemical processing, this hydroxylation. And then we have a surface which wants to attack, or which wants to touch these molecules with this tripod. And then there's a chemical reaction where the H, the yellow ones, react with the chlorine ones. And you know what happens then, of course, we have chlorine acid. And this is a gas which goes away. And then we attach, in this way, our molecule to the surface. We create somehow hairs on it, or I would better say a field of grains, like a field of wheat or something like that. So that is the idea. And now the interesting thing is, you will say, but this is also somehow lotus. You say, no, this is not lotus. But why not? Because the size is different. You see here, we can steer the height or the length of these molecules by chemistry. And if we add some silane molecules, we make it longer or shorter. So in this way, we can steer the wavelength at which we have a cutoff, or where stray light begins. So here we are not in the range of, we are maybe almost no more in the range of Rayleigh straying. Definitely we have no Mie stray light. This is the idea behind. So this is theory. Let us now come to reality. Does it really work? The first question was, is there any change with respect to classical non-coated surfaces, clean boats? This was a sample without the coating, and this was the effect we had. This was typically a transmission of 98%. There was an anti-reflective coating already on it, a commercial one. And here is a sample with our no-coat coating, and let us compare them. So you see there is almost no difference. There's some regions where it appears to be a little slightly better, others where it is slightly worse, but in more or less it is acceptable. So this convinced our industrial partner to go further. So we had delta in transmission between smaller than 0.5% between in the visible range from 400 to 700 nanometers, which was important at that kind. So the test of repellence is typically done with a contact angle measurement. So we tried to figure out the static contact angle. Contact angle is easy, just to put a drop on the surface and you look what is the angle of the drop. Is it a drop which is like this or totally flat? So we tested 3 different liquids, water, HO2. We tested one very with your very strong dipole, which is this iodide CH2I2, and a totally organic material, which is a C10H12 product. And we just put a drop on it and measured the contact angle. And you see here, in compared to other already existing repellent coatings, there was, for example, this polysiloxane coating, there was a polyfluorine coating, there was a sputtered PTFO coating, and there was our no-coat coating. We can easily see the contact angle here was, for water, the highest. It's 123 here, whereas this is 110, 92, or 90. And also for these very dipolic materials, here we have 78, 73, 71, and 69. So we see definitely here this is more repellent. And also when it comes to organic products, as you can see it here, is 49 compared to 22 or 20 something and 10 degrees. This showed us we are on the right way. Our coating works, and it has a certain other advantage. As I said before, we wanted also to use this kind of process for diffractive optical elements. Let us have a look. If we have diffractive optical elements, gratings, typically they look like that. If we do it with a classical salinization process, using the same chemistry, however, applying it not in a chemical process, in a chemical vapor deposition process, by using here a typical physical vapor deposition, the following effect will happen. So this is like snow, which snows down, but you don't know what is snow. This is difficult for you to explain. It's a precipitation of frozen water crystals coming down on the surface and makes small, nice effects on, let's say, a garden fence. He knows, or those people having been to Europe or to places where are snow, they know how it looks like. It really looks a little bit like this. So this is nice. However, what happens when pollution comes? Yeah, we have our dust particles sitting on the side walls, and they will create, of course, stray light. So lateral contamination, so this does not really help. However, when it comes to CVD processes, the chemical reaction will always take place where there is a chemical possibility independent of the shape of the substrate. So that's the situation we have here. And here we have no lateral contamination. So that's an idea we had already years before, and that's why we put it in patent. This was patented by my colleague and mine in 2002. And since then it has become a process in industry which is today used. So let me now summarize also this aspect. So the results and experience obtained with this no-coat coatings clearly show a large potential to realize a new type of dust repellent and non-wetting coating, especially in the field of precision optics. So just saying precision optics in opposite to glasses like this. This is not precision optics, this is just ophthalmology. Clear process technology advantages make no-coat to be very interesting for industrial environments, especially when it comes to diffractive optical elements. This no-coat type shows process and chemistry inherent advantages since the surface is coated independent of shape and orientation. And the current process unfortunately works only with SiO2 because our chemistry was oriented for SiO2 applications. However, for the future, we should focus on new chemistries in order to use other substrate materials. But this is a chemical thing. I'm not a chemist, so I cannot work in this field. But possibly there are chemists here in the room. We could try to figure out if there is some interest of research collaboration. However, until now, we don't have enough complete understanding of the relation between the surface roughness and wettability on one side and scattering on the other side. This is another research topic I'm currently focusing in with the companies in Germany. And also this topic would be an interesting topic for collaboration. So let me at the end thank also the partners of these projects, which are Michael Gale, Mark Schnieper, Jens Gobrecht and Christian David, Patrick Hoffmann, Martin Geis and Fritz Schoch. So thank you very much for your attention, and I hope you got some insight and some feeling of nanotechnology. And don't forget, a nanometer is a dwarf meter, 10 to the minus 9. So if your daughter, your son, your sister, your brother, the younger, will ask you, I know what is nanotechnology. Nanos is Greek and means a dwarf. Thank you.
Thank you, sir. Now proceeding to the questionnaire session. Any questions?
So your discussion was confined to only 2-3 material items.
Yes.
Why can't we extend this to other type of materials also?
Yes, definitely. It can be extended to all kinds of applications. There might not be optical. There can be also mechanical. There can also be chemical or mechanical or electronic. Of course, there could be a lot of applications. I was focusing here on optics because this is my field. But of course, also in optics, there are other applications, especially when it comes to biomedical applications. Especially this last mentioned Nocco wetting coating was a coating we had initially planned for operation microscopes. Operation microscopes have a big problem because you may know the lens is opposed very close to the place where the operation takes place, and often we have liquids spilling out and spilling on the lens. And then this requires afterwards an immense cleaning effect, a cleaning process, which makes operations very expensive. So the idea of the producer was initially to use such kind of non-wetting coatings to avoid such kind of situations.
Did you use clean rooms or it was done in open?
Partly. Okay. Let's say the calcium fluoride process had been made in clean room. Most of the measurements have been made not in clean room, but in flow box environment. I don't know if you're familiar to this. This is let's say, a soft or easy realizable. So it's a soft, it's a clean room class, 1,000 can be reached.
Now it appears that the whole thing is heavily dependent on your capability in handling the experiments. It's highly experimental, right?
Yes.
So as you try to make a product out of that, how do you make sure that there is a repetition possible of the quality? How do you ensure the quality?
Yeah.
How is it that ensured?
Yes. That's as I said, it was a project we did together with industry. So people in industry, they have a totally different thinking than researchers. Researchers were just a result. And people in industry want a certain quality assurance for the processes. That's why we always focused on that process. As I said, these etching rates, it took us months to have the right etching rate because the materials and the surfaces, the treatment, the pre-treatment of the surfaces were a big issue to be investigated. And that's something I want always to say if it comes to nanotechnology. Keep your eyes on the surface. You will never get an understanding if you don't have the feeling for the nanosurface. And then the question is even, what means contact? Do I touch a surface or don't I touch not with hands, even with a solid body? What is contact? This is a philosophical question even.
Yeah, yeah.
It is a contact, in my understanding, means we have an interaction between two solid body, and if there is a change in shape or in energy, this was some kind of contact has happened. But the contact must not be a physical contact in our macroscopic thinking. It could have been also a contact which is separations of several tenths or twentieths of nanometers.
I wonder how the nature is able to organize this. For example, we have been talking about the moth, the moth eye.
Yes.
There also they would have had these sort of nanostructures.
Yeah, correct.
Designed of fine gratings.
Yes.
And the qualification would have been very high because it's working fine.
Yeah.
But for pathological reasons, they would have done a good job. They would have come up very well. I just don't know how the nature would have achieved all these things.
Yeah, evolution is the right word for it. It took nature, I don't know how many millions of years in order to produce such, and of course the Spirit of God, to have these excellent structures. But this is exactly what I'm admiring always when it comes to nature. I see such kind of moth structures and say, wow, we had this now theoretically this idea, but nature was before us. They had already these ideas. And especially not only when it comes to optics, but also fish. So our sharks, fish, they have on their skin a special surface which is structured and done nanometrically in order to make them to swim easier or with less resistance. But you are totally right, moths have this effect since I don't know how many million years. But you know what helped them to develop these eyes were their enemies. You know, the moth, they need these eyes for two reasons. The one reason is to see at night, because they are flying around when it's dark, where there's not so much light. And secondly, their enemies are the birds. And the birds, they have a special type of finding out where is something to eat. They have their eyes. And they look with an eye of another animal which reflects. However, if there is no reflection, they cannot see them. So they say, okay, this is just a leaf or from a tree or I don't know. So they can avoid being picked up by birds.
It's a camouflage, effectively.
Yeah.
Any more questions?
Sir, you have already told about anti-reflecting materials that can reflect lights of wavelength near 193 nanometers, no? So,
yes.
So where do we find applications for these narrow band reflecting materials? That is it is reflecting only a small narrow band light, no? That is near to 193 nanometer. Rest of the lights of wavelengths are getting into it, getting passed through it, no? So where do we find applications for these type of materials? And can we call those materials as anti-reflecting materials?
Yes. As you said, the current application I showed you was mainly an application in the visible or in the near DUV range, 193 nanometers. There are ideas to go beyond that, but this requires then, keep always in mind, 193 nanometers divided by 2 would result in 95 nanometers, roughly. And this would be really at the limit of what we can currently create with standard means. It is possible, but it is always a question of money that you will invest for it. For the semiconductor productions, there are already in this range of some 10 nanometers, 20, 25 nanometers the node. But there, the technology is very, very high. I don't know if you are informed about the current semiconductor production processes. This is an extremely expensive process which works only if you have large quantities. There are not very much producers in the world which work at these with these machines. There is one producer is Intel, of course you know, and there is ASML. You never heard maybe about this company ASML. They are producing machines to produce semiconductors. And these people, they tell me that if you don't have batches of several hundreds of millions a day or a year, you will not be economically successful. But you are right, we could apply this also for other dimensions.
Thank you, sir.
The gratings are tuned for a specific narrow band,
Yeah.
as my
Yeah,
friend asked.
Yeah.
See, if you want to camouflage the human side, because human, normally we see over a very